Okay, welcome back everyone. In this video we're going to talk about electric field superposition, which is a fancy way for saying how to add vectors. And in this example we're going to be solving problem 61 on page 533, and this is a 3-dot problem, but we're going to show that it's really not that bad. We want to find the electric field at the center of the square of charges shown in this diagram. So we have 4 charges, 2 negatives of 10 microcoulombs and 2 positives of 5 microcoulombs, and the square has sides of 10 centimeters each. And we want to find the electric field at point P, which is right at the center. So the first thing that we need to do is think conceptually, what are all of these charges going to be doing at the center in terms of electric field? So remember, we put down a tiny positive test charge and say, what will that do? And we know that the positive will be attracted to the negatives, and so those will be the 2 fields from the negative 10 microcoulombs, and it will be repelled from the positives. So there will be, and I'm not drawing them all in the same place, these are all at point P. The fields from charges 3 and 4 will go away from charges 3 and 4. So this is going to be an adding vectors thing. Now, one thing that we can do to make this a little bit easier is try to find the radius r for this, and we know that this triangle has sides of 0.05 because it's halfway of the 0.10. So this means that we have a radius here of 0.05 root 2, and if you plop that into a calculator squared, it's equal to 0.005 meters squared. So r is 0.05 root 2, and that comes from the geometry of the situation. So there's r and 0.05 on a side, and it's a 45, 45, 90. Okay, so that's one thing that makes this a little bit easier. And so what I suggest is that we calculate the electric field from charge 1, which is actually equal to the electric field from charge 2 as long as we're talking magnitude. So it's going to be kq over r squared, and this is why I suggest calculating r squared first. So we have 9 times 10 to the 9th, and we have 10 microcoulombs. Once again, notice that I'm not putting in the negative sign. I'm using the diagram to draw the field lines. And then 0.005 meters squared. And this works out to give us electric field from 1 and 2, basically 1.8 times 10 to the 7th newtons per coulomb. We can do the same thing for charges 3 and 4, and they'll have similar field strengths. That's going to be kq for them over r squared. And I'm going to write this out, I really don't have to. Now it's 5 microcoulombs, and it's still r squared is 0.005 meters squared. So that means that we've got pretty much half, so 9.0 times 10 to the 6th newtons per coulomb. Okay, so that's actually the toughest part. Now we just have to take these 4 field vectors that we have, and I think the easiest thing to do is components. So for example, let's look at E3. Okay, so E3 is kind of this guy right here, coming from charge 3. Well, we want to split this up into E3x and E3y, and it turns out we have a 45-degree angle, so it's just going to be E3 times the cosine of 45, or E3 times root 2 over 2, and this is going to be E3 times the sine of 45, which amazingly is also root 2 over 2. So that's going to make this calculation a lot easier. We just need to try to keep track of our directions. So I'm going to make a table, and in this table I'm going to try to put all 4 of the fields Okay, so we're going to have E1, E2, E3, and E4. And we know that these two are 1.8 times 10 to the 7th, and that these two are 9 times 10 to the 6th, and now we can just split them up into x and y components. Okay, so just as an example, E1 is going up and to the left, so it's going to have a negative x component and positive y. So it's going to be negative 1.8 times 10 to the 7th times root 2 over 2, and the y component will be positive 1.8 times 10 to the 7th root 2 over 2. Okay, E2 is going up and to the right, and E2 is going to be plus 1.8 times 10 to the 7th root 2 over 2, and its y will also be 1.8 times 10 to the 7th root 2 over 2. By the way, I just realized that I actually had circled E2 and called it E3, but it's the same thing, going the same direction. So you can already see that these x components are going to cancel and the y's will add together. And the same thing for E3. E3 is going actually up and to the right. Okay, so that's going to be positive 9.0 times 10 to the 6th root 2 over 2, and positive 9.0 times 10 to the 6th root 2 over 2, and then E4 looks something like this. It's up to the left, so it has a negative x component and positive y component. And again, the x components cancel out to give us a total field, or E totes, in the x direction of 0, and in the y direction I actually calculated this out previously, but it's about 3.82 times 10 to the 7th newtons per coulomb. And so that is our final answer. The electric field just points upwards. In other words, all of the x components for the 4 pieces of the field cancel out and leave us with an overall y component. And it's just as easy as that. When you have different angles, different charges, it gets a little bit more complicated, but the process is exactly the same. And we've studied this before when we added force vectors, so this should not be too new. This might be review.